go ahead with the next talk by Masoud Kamgarpour, who will talk about Langlands correspondence for hypergeometric local systems. Please go ahead.
Thank you very much for organizing this conference and for everyone for being here. So today I want to talk about joint work with Lingfei Yi about geometric Langlands for hypergeometric local systems. And I'm going to start by a leisurely introduction to hypergeometric world, because that's not what perhaps usually algebraic geometers or representation theorists think about. A hypergeometric series, or what's called a generalized hypergeometric series, is something that looks like this. So you just take the geometric series, but you put in some coefficients. But these coefficients are not arbitrary. We require that there exist polynomials A and B such that the successive quotients is the value of this polynomial at n. So beta n plus 1 divided by beta n is the value of an divided by bn. And the study of these, so this kind of series appeared first in the work of John Wallis, who was a mathematician contemporary of Newton and Leibniz. So here's a beautiful theorem of Wallis from around 1650s, I think. So, and the theorem says that pi over 2 is the product n equals 1 to infinity of 4n squared divided by 4n squared minus 1, which is same as 2n times 2n divided by 2n plus 1, which more commonly is written like this infinite product. And it's an entertaining exercise. Try to prove this. It's not trivial, even after a few hundred years. So the successive quotients here are, of course, they look like this, which is a quotient of polynomials for appropriate A and B. So this is an example of sort of hypergeometric quotients coming into play. And so right around when Wallis sort of started working with these kind of things, Newton also got interested in it. And he started working with some hypergeometric quotients and hypergeometric fractions in his work. So I digged around, and you can actually go to Cambridge University and look at Newton's letters. And he has a massive number of letters. So this is a letter of Newton from October 26, 1676. So the letter is addressed to a fellow by the name of Oldenburg. So Oldenburg is the first head of the Royal Society. So this is right after the Reconstruction, when King Charles II came back to England, and they built the Royal Society, and Oldenburg was the head of the Royal Society. And the way they used to communicate back then, so Newton writes this letter, and so he keeps writing letters. So if you notice at the beginning, he says, 2 days ago, I sent you a letter that was intended for Mr. Leibniz. So I've highlighted, some of these. And so he would send the letters to Oldenburg to be forwarded to Leibniz. And they would just do this like all the time. Like in a week, they might send each other like 3 letters through Oldenburg. And the reason they would send it through Oldenburg was that this is sort of proto peer review. So people would just send him letters, and he would send it to other people to be peer reviews. And that gave sort of rise to the first peer-reviewed journal, which is the transactions of the philosophical transactions of the Royal Society. So this is really fascinating history. And you can see Newton here sort of talking about quotients that are hypergeometric in nature. So he's is discussing these. I'm not sure exactly why he was doing it, in what context, but you can see him discussing these kind of things. So this is about hypergeometric series and hypergeometric fractions, but the hypergeometric function was, its systematic study was first, is essentially due to Gauss, although Euler had also a lot to do with it. And the most famous of these is a function that looks like this. It's denoted by 2f1, a, b, c. So all of these are complex numbers. And it's an infinite expansion, which looks like this. So this is commonly called Gauss's hypergeometric function, because he considered it as a function of complex variables and showed that it's holomorphic near zero and satisfies nice properties that I will talk about more in a minute. So this is 1 plus AB divided by C. And here, this notation, this is the Pochhammer symbol. So which looks like this. And so this is the Gauss's hypergeometric function. And it satisfies many amazing properties. So I just sort of copied some of them from Wikipedia just for you to see. So here's some examples. So some rather easy ones are what happens if you put in some special values like 1, 1, and 2 for A, B, and C, then you essentially get ln. Or if you put A, B, B, then you get 1 minus A to the power minus A. And you also get arcsine, and you get, beautiful identities. Here we have Euler transformation, Pfaff transformation. So this also gives you a list of people that were working on this, which is sort of who is who of great mathematicians. And here's a beautiful transformation, highly non-trivial due to Kummer. And here's a beautiful infinite fractions, continuous fraction expansion, and this is due to Gauss. So there was plenty of identities that people were interested in. They were proving properties of these. The way I like to view hypergeometrics has to do with their geometry. And the geometry of hypergeometrics really came to forth by Riemann. So Euler was first wrote down the differential equation that this hypergeometric function satisfies. So this differential equation looks like this. So it's a second order ODE. And when you write this ODE, you see that you have poles at 1 and 0. Okay. So this is so we consider this as a differential equation, but it has singularities at 0 and 1. Okay, so Riemann's revolutionary insight, I mean, he had several insights in just one paper that he considered this. So first of all, he said that we should study this equation not on C minus a point, minus 2 points, but on P1 minus 3 points. So this is the birth of Riemann's sphere, was exactly for studying this equation. He invented the Riemann sphere and considered the singularity around infinity as well. Well, showed that it's singular and studied the singularity there. So this is birth of Riemann sphere. Secondly, Riemann advocated that we should study the local system of solutions to this differential equation as a geometric object over this punctured Riemann sphere. And this is sort of the birth of the notion of local system. Thirdly, so let's call this local system something, let's call it L, and Riemann proved that L is rigid. And this was also a key notion. He didn't call it rigid, we now call it rigid. So this is, so what that means, i.e. completely determined by local monodromy at 0, 1, and infinity. Just to appreciate how special this property is, you should compare this. I mean, this was also the birth of Riemann-Hilbert correspondence. Which says that a local system is completely determined by its global monodromy, by its total monodromy. These local monodromies sit inside.
Yes.
I was talking about the notion of rigidity. So as I was saying, this local system is rigid. So what that means is completely determined by local monodromy. So in other words, its global monodromy is completely determined by what happens at the three singular points. Okay. Now, let me mention that there's a generalization of these to higher ranks. Generalization of the hypergeometrics to the higher ranks. So this is typically denoted. So the these two F1, the corresponding local system has rank 2, and that's just because the ODE is a degree 2 ODE. So there's a generalization to rank n local systems, which is again a rigid local system on, so this is a local system on P1 minus 3 points. Okay, and to specify it, we need the 2n complex numbers, which I denoted by alpha 1 to alpha n and beta 1 to beta n. And the local system is, so generically, if alpha i's are not equal to beta j for all ij, then the corresponding local system is irreducible and rigid. And let me tell you about the monodromies. So the monodromy at 0 is given by a regular matrix. So it's a regular matrix. It's of course a conjugacy class, but I just say matrix with eigenvalues e to the 2 pi I alpha j's. And similarly, monodromy at infinity is the same thing, but with the alpha j is replaced by beta j's. Okay, and then the monodromy at 0, at 1, is a pseudo reflection, or sometimes called complex reflection. So what that means is that it's given by a matrix that looks like eigenvalues are 1, except one eigenvalue, and I think this is like product of e to the 2 pi I alpha I divided by something like that, depending on how well normalized it. The exact numbers is not very important right now. I just want to give you the shape of the monodromy. So for instance, if all alphas are 0, then you see, which is allowed, then you see that the monodromy at the 0 will be the principal unipotent conjugacy class. Any questions about that?
You're requiring it to be regular with those eigenvalues. So if they're all 1, then it should be a single Jordan block. Okay, I understand.
Yeah, exactly. So I'm requiring it to be regular. So if all the eigenvalues are equal, that means it has to be one Jordan block. So it's the principal unipotent. Next, I want to talk about realization of hypergeometrics via convolution. So, I mean, before saying that, this is a bit of a tangent to tell you about the motives. One way to view our work is that we give another realization of hypergeometric local systems, namely the realization via Langlands duality. Okay, but before doing that, because this is about motives, let me tell you how the motivic picture came in. So let's look at the Euler. There's a beautiful Euler integral for hypergeometric functions. In particular, let me write it for Gauss's hypergeometric function. And the Euler integral goes like this. And you see from this integral the relationship between the gamma function and the hypergeometric function. So it's this beautiful relationship. Okay, and if your name is Nicholas Katz, you stare at this Euler integral and specifically at this term x1 minus x, and you're reminded of convolution on GM, convolution of D modules on GM. So basically what this led Katz to was to give a definition of these or a realization of these local systems via convolution. So by that, I mean, so recall that we have 3 maps from GM times GM to GM. So 1 is multiplication and 2 projections. And convolution is defined by, well, let's take lower shrift. You can also take lower star. Convolution of 2 sheaves on GM. So what Katz showed is that this local system with parameters alpha 1, alpha n, and beta 1. So first of all, he showed that this can be written as a local system, as convolution of rank 1 local systems. And these rank 1 local systems are very simple. You can explicitly describe them. Okay, I'm not going to do it right now, but the point is this allowed him to do 2 important things. First of all, once you see this one-dimensional thing, 2 consequences. First of all, he was able to define the characteristic P analogs, because these rank 1 local systems have very simple things, and he was able to guess what the characteristic P analog of those are. And then he defined hypergeometrics in characteristic P via convolution of some rank 1 sheaves. Okay, so these are Lingfei et al. Sheaves, if you wish, in characteristic P. So and secondly, he showed that if alpha I and beta j's are rational numbers, so remember that I told you the monodromy. So being rational means that this has quasi-unipotent monodromy. And he showed that in this case, these are motivic. And the way he showed it is exactly by using this convolution. And then he reduced the problem to a rank 1 local system, which is pretty, and then explicitly he realized the motive for this rank 1 case, and then explained how convolution preserves this sort of motivic property. So this should be compared. So he later used convolution to actually show all rigid connections on P1 are motivic. So this should be compared with Simpson's conjecture that all rigid quasi-unipotent local systems on arbitrary dimensional varieties are motivic. So Katz has proved the rank 1 case by thinking really hard. I mean, the starting point is really thinking really hard about hypergeometrics. So any questions about that?
There's a question by Jordi in the chat who's apparently confused that the hypergeometric local systems have singularities at 0, 1, and infinity, but the convolution only looks like it is singular at 0 and infinity.
Right. So when I talk about convolution, it's actually convolution of D modules, right? Because we have to go to the derived category. And then the D modules may have singularities anywhere. So, but the point is that he shows that this output, once you go to, once you apply lower shriek, a priori you can get a complete mess, but he shows that away from 0, 1, and infinity, you actually have a local system when you apply it to the correct sheaves. All right, so now I'm going to switch gears and talk about geometric Langlands. So what does geometric Langlands want? So the basic objects of study here is that you have a curve, a reductive group, and its Langlands dual group. And geometric Langlands wants to establish a duality between local systems on X and some objects, local systems with G-check local systems on X and some sheaves on a moduli of G bundles on X. Okay, so it's some sort of duality, and the core conjecture of the field can be phrased as follows. So for this, you can see, for instance, Benzivi and Nadler's paper on Betty geometric Langlands, where they explicitly state this, but it was sort of known to people and first formulated by Lamont. So to every irreducible G-check local system, L on X, one can associate an irreducible perverse sheaf on bun GX. Let's call this perverse sheaf something. So A sub L, such that A sub L is a Hecke eigensheaf with eigenvalue L. Okay. So now, just a comment before we move on is that if your curve is not complete, then bun G is not quite enough. You need to put level structures at the points that are missing from your complete curve. Okay, and we will see that in a minute how that comes into play. And so the main theorem, our main theorem with Lingfei is that we prove this conjecture for hypergeometric local systems by explicitly constructing the corresponding Hecke eigensheaf. So the Hecke eigensheaf, whose eigenvalue is a hypergeometric. Okay, now I have a slide about, just tells you a bit of a history to put this in context, but I don't want to write it in the interest of time. So let me just show you this. So suppose first is X is complete, then, so the story of geometric Langlands goes back to Deleuze, who gave a beautiful proof of geometric class field theory, the unramified geometric class field theory in the 70s. Essentially, the proof of class field theory, unramified class field theory, came down to the fact that P1 is simply connected in characteristic P, or any characteristic. And then Drinfeld saw this proof and generalized it to GL2. But he was thinking about the sort of classical Langlands correspondence, where on the right-hand side, so he didn't formulate things in terms of Hecke eigensheafs, but that's essentially what he did. He constructed Hecke eigensheafs associated to rank 2 local systems. And Lamont took this and sort of crystallized the idea of a Hecke eigensheaf and formulated a conjecture for GLN, which was proved by Frankel, Gates-Corey, and Villone in around 2000. Okay, and if G is not GLN, then much less known is about this conjecture. If you're over a complex numbers, then the best we've done is the book of Bailinson and Drinfield, where they construct Hecke eigensheaves for certain local systems called OPERs. And let me also mention in passing that if you don't require L to be irreducible, then you have to go categorical, infinite categories, etc. And so this is the sort of thing you see in the work of Arinkin, Gates-Corey, etc. Because then to a non-irreducible local system, one has to associate a category of Hecke eigensheaves. Okay. And if X is not complete, which is our situation, because remember, our local system is on P1 minus 3 points, then much less is known about Hecke eigensheaves. So, so this is the case that we're treating, and you see we're working on P1 minus 3 points. But yeah, in this case, much less is known. So there's more details about what is known in our paper with Lingfei. Let me move on and let me tell you how construct this Hecke eigensheaf. And the how has to do with rigidity. So here there's a program of that emerged in a beautiful work of Heinloth, Engo, and Yon, and was further crystallized by Jiwei Yon in CDM volume 2013. So for understanding a geometric Langlands correspondence in the rigid case. Now, I should mention that the rigid case is extremely special. So for instance, it is known that rigid local systems can only appear on P1, and there's and on an elliptic curve. And on an elliptic curve, there's only finitely many of them. So, so that's all we can treat from these, but this is already quite a bit of stuff for which we don't know how to construct the Hecke eigensheaves. So they sort of outline the program. So what does that look like? So first, one looks at local monodromies of L, your local system, at the singular points. Let's say x1 to xm. And this is, let's say we're working over P1. As I said, that's where most of the action for rigidity happens. Okay, second, you have to guess the correct level structure based on the monodromy. So you're seeing some monodromy, and you have to use a bit of knowledge about local Langlands, etc., to guess what the correct monodromy should be. The correct level structure should be on the dual side. And by the way, this case that we're considering is for G equals to GLN for hypergeometrics at the moment. We're just considering G equals GLN, so the dual is the same as G itself. Okay, third is to prove that there exists a unique appropriately equivariant perverse sheaf on Bun G, so Bun and P1 with level structure that we put in at X1 and Xn. Okay, so this is what they call rigidity in the automorphic side. So remember, Riemann essentially defined the notion of rigid for a local system. And if you believe in Langlands duality, that means that there is a notion of rigid on the automorphic side as well. So so Heinloth, Engo, Yon sort of axiomatize what that rigidity should mean. So what it means is that there's a unique perverse sheaf, appropriately equivalent perverse sheaf on on bungee equipped with some level structure. Okay, and their theorem that we use is that if you're in this situation of rigidity, then your perverse sheaf is a Hecke eigensheaf. Okay, and finally, you have to prove that the resulting Hecke eigenvalue is the local system that you started with. Okay, so we have a 5-step program. So first, you need to understand the monodromies of your local system. Then you have to guess something. Then you have to prove something. But then you have something for free. Namely, they tell you that what you get is then a Hecke eigensheaf. So that means there is a Hecke eigenvalue. And so then you're left with proving that this eigenvalue is what you wanted, that your setup actually works. Okay. Now, the most beautiful, I think, application of these ideas was given by Yun. So this is a bit of an aside from our work, but since this is a conference on motifs, one must mention this. So what Yun did, he said, so there was a question of Serre, which was open for a long time. And the question was, is there a motive with exceptional Galois group monodromy being, say, E8 or E7 or something like that? Because Katz had shown that actually the monodromy of some hypergeometric sheaves can be G2, which was kind of a surprise. But then the natural question was, well, can one get something like E8 as a monodromy of a motif? And what Yun did, he sort of turned this machine around. He said, okay, he sort of carefully constructed a Hecke eigensheaf using these, whose Hecke eigenvalue was not anything that one already knew, but something really new. And he showed that the monodromy of the Hecke eigenvalue is E8. Okay, so he solved Serre's problem. So see, for instance, Yun's paper on motifs. Okay, by the way, Jiwei Yun is teaching a course on this in Arizona Winter School next year. In case some of the younger people are interested in this, they can learn more about it. So I will tell you how we implement this program in our situation. So how does this look for hypergeometrics? So I'm going to work in the Elatic setting. You can also work in the DRAM setting. So instead of complex numbers, we will be working with alpha I and beta i's. We'll take them to be characters of multiplicative group of a finite field. So what we need is, so then the Katz defined the corresponding, so this is what I was alluding to earlier, that Katz defined the characteristic P analogs of hypergeometrics. So this is the input data that you need is characters of a finite field. So I call these Elatic hypergeometric sheaves. Okay, so all right, to implement that program, we need to figure out what sort of level structures we need to put. So we need level structures at 0, 1, infinity. At 0, we're going to put the Iwahori. And the reason we put the Iwahori is exactly the reason that I was telling you. In some cases, we have the principal unipotent monodromy. You know, Iwahori and principal unipotent are closely related. So it's believable that we should put this. And in fact, this appeared in previous works as well. So we put the Iwahori subgroup. Let me remind you. Well, okay. And then these alphas give us a character of Iwahori. Similarly, at infinity, we put the Iwahori. So, for instance, if alphas were trivial, then we don't need this character. Okay. So at infinity, we put again Iwahori and the character beta So these level structures, so the level structure is going to be the Iwahori, or maybe the unipotent radical of the Iwahori. And the characters are going to tell us the equivariance. What kind of equivariant perverse sheaves should we consider? Okay, so the remaining thing is at 1. So what should we put there? Remember, the monodromy there was pseudo-reflection or complex reflection, which means all the eigenvalues are 1 except 1. And this suggests, if you know a bit about Langlands duality, this suggests that we put the mirabolic subgroup. So we put the parahoric that corresponds to the maximal parabolic. So remember, this is the maximal parabolic. And what's interesting, actually, for technical reasons to do with central characters, we indeed have to use the mirabolic subgroup. So this is the miraculous parabolic, this is the subgroup known as mirabolic. So that's what we have to put at 1. Okay. So then our main result can be reformulated as follows. So the heart of that day, what we do is the following theorem, that there exists a unique mu alpha, mu beta. So this mu is the character sheaf corresponding to alpha and beta. So this is character sheaf on I times I. So there is a unique mu alpha mu beta equivariant perverse sheaf on bond N equipped with these level structures 0, 1, and infinity. By the way, the Iwahori level structure just means you're putting a flag, okay? Actually, each of these can be just described in terms of flag, and this is how, so Iwahori means complete flag, and this mirabolic subgroup is sort of the opposite of the complete flag, okay? So it just has one part. But actually, it's much, much better to describe them using Brouhatit group schemes, and that gives much cleaner exposition. Okay, so let me not get into how we prove this theorem, since there's no time. So let me just end by saying a few further directions and some things that I didn't discuss. So and this is to make up for the time lost due to the storm. So I talked about functions fn-1n, those hypergeometrics. So that suggests that there is, these kind of hypergeometrics as well. Now, the interesting thing about these hypergeometrics is that the local system, we treat these in our paper as well, the local system has wild singularity. So it's no longer tame like the previous case. And what intervenes in constructing the automorphic sheaves is finite gradings of the algebras, which we also saw in so this work of JKU and Prasad, etc., all appears here. And we saw that in the talk of Ting as well. Okay, so another point is that some hypergeometrics have monodromy, not the full group GLN, but some subgroup, like the kind of subgroups that can appear is SPN, SON, or G2 in the case that n equals to 7. So let's call this G-che. Now, geometric Langlands says that you should be able to get Hecke eigensheaves on bond G, where G is now the dual group. So together, Jacob, we construct these the corresponding Hecke eigensheaf on bond GLN already, but now we're constructing them on bond. And that's a highly non-trivial exercise. This is part of what goes by the name of Langlands functoriality. So this is just a special case of functoriality where for instance, if you look at SPN going inside GLN, then that's telling you something on the Langlands dual side. So that all goes by the name of Langlands functoriality. And finally, could we have hypergeometrics, more general versions of them with monodromy, say, E8? I told you that GUAU has constructed some sheaves with monodromy E8, some motives, but they were not hypergeometric or sort of any generalization of them. Could we do this within the framework of hypergeometrics? And actually, this is partly done by Heinloth, Ngo, and Yoon in the setting of what they call Klusterman sheaves. And actually, Klusterman corresponds to the case, I think, that you're dealing with the function f0n, okay? So the extreme case. But the cases in between, we don't know still. So that we're sort of investigating that, if we can define something with exceptional monodromy. Okay, I think it's time for me to stop. I hope that despite all the setbacks with the power, etc., that you got something out of it. And I thank you for your time.
Thank you very much for this very nice talk, despite all the influence from storms.